The topic that I am going to discuss is chirality, the handedness of molecules. We all know already that there are two types of stereoisomers, these namely the cis and the trans isomers of certain distributed cycloalkanes and appropriately substituted alkenes. Recall that stereoisomers have the same connectivity of their atoms but a different orientation of their atoms in space. In this figure, it summarizes the different types of isomerism. So, isomers are either stereoisomers and constitutional isomers. So, if these isomers have the same connectivity, these are considered as stereoisomers, while the isomer with different connectivity is said to be constitutional isomers. Further, stereoisomers are classified into achiral and chiral stereoisomers. If without stereocenters, the stereoisomer is achiral, and if the molecule with stereocenters, it is said to be stereoisomer, which is chiral. So, the chiral further classified into enantiomers and diastereomers, while achiral is classified into either cis and the trans isomerism. Isomers are said to be different compounds that have the same formula. And there are two general types of isomers. These are, as what I've said in the previous slide, constitutional isomers and stereoisomers. When we are telling everybody that constitutional isomers are the same molecular formula but different constitution, or when we are talking with constitution in chemistry, the order of the connectivity of the atoms. While when we are talking with stereoisomers, they have the same molecular formula and the same constitution but different spatial arrangement of atoms in space. Just like what we have in this example. Although these two molecules below have the same connectivity, but they are not considered as the same molecule. They are not identical. So, they are considered as stereoisomers. Focus our attention on the cis and the trans, wherein the location of the two CH3s of the cis and the trans 1,2-dimethyl cyclohexane. In this cis 1,2-dimethyl cyclohexane, both groups is in the same side of the ring. Both CH3 is on the top and the hydrogens are here. While in the trans 1,2-dimethyl cyclohexane, both groups are on the opposite side. This one, and then the hydrogen and another hydrogen. So in order to give these compounds a unique names, we use, of course, the prefixes that we have learned in our previous lectures, the cis and the trans prefixes. To maintain, of course, the orbital overlap in the pi bond of the carbon-carbon double bonds cannot be freely rotate. Although the two molecules below have the same connectivity, they are not identical. That is why they are stereoisomers, as what we have in this slide. The cis and the trans dimethyl cyclohexane, and in this case, we have the cis and the trans 2-butene. In this example, of course, this is a butene or an alkene. So notice that the 2CH3 here is located in the same side of the pi bond. And while this one, of course, is on the opposite sides. That is why they are not identical and they are said to be stereoisomers. Recall that stereoisomers are with the same molecule or molecular formula and constitution, but they have different spatial arrangements of their atoms in space. Enantiomers are non-superposable mirror images. As an example of a molecule that exists as a pair of enantiomers, we will consider the structures of 2-butanol. Here, the original image and the mirror image. So the significance of enantiomers is that except for inorganic compounds and a few simple organic compounds, the vast majority of molecules in the biological world shows this type of isomerism. Furthermore, approximately 1/2 of all medications used to treat humans display this property. As an example of enantiomerism, let us consider, as what I've said, the 2-butanol molecule. As we discuss this molecule, we will focus on the carbon number 2, the carbon bearing the OH, this one. The question is that what makes this carbon of interest is the fact that it has 4 different groups bonded to it. The hydrogen, the CH3, the CH2CH3, and the OH. This structural formula does not show the 3-dimensional shape of 2-butanol or the orientation of its atoms in space. So to do so, we must consider the molecule as a 3-dimensional object. On the left here is what we will call the original molecule and the ball and stick model of it. In this drawing, the OH group and the CH3 group are in the plane of the paper. The H is behind the plane, showing a broken wedge, this one. And the CH2, CH3 is in the front of it, shown as a solid wedge. So in the middle is a mirror. On the right side is a mirror image of the original molecule along with a ball and stick model of the mirror image. Every molecule and, in fact, every object in the world around us has a mirror image. So the question now we need to ask is, what is the relationship between the original molecule of the 2-butanol and its mirror image? So to answer this question, we need to imagine that we must pick the mirror image and move it in 3D space in any way we wish. So if we can move the mirror image in space and find that it fits over the original molecule, so that every bond, atom, and detail of the image or the mirror image will match exactly the bonds, the atoms, and details of the original, then the two are said to be superposable. In other words, the mirror image and the original represents the same molecule. They are merely oriented differently in space. If, however, no matter how we turn the mirror image in space, it will not fit exactly on the original with every detailed matching, then the two are non-superposable. They are different molecules. Again, if the image are superposable, then therefore they are the same molecules. But if the molecules or the image are non-superposable, no matter what happened, they are different molecule. One way to see the mirror image of 2-butanol is not superposable on the original molecule is illustrated in the following drawings. Imagine that we hold the mirror by the C bonded to OH and rotate the bottom part, this one. We make sure that the rotation is 180 degrees. So the OH group retains its position in space. But the CH3 group, which was to the right and in the plane of the paper, remains in the plane of the paper but is now to the left. Similarly, the CH2, CH3 group, which was in front of the plane of the paper and to the left, is now behind the plane and to the right. Now, move the mirror image in space and try to fit it on the original molecule so that all bonds and atoms matched. By turning the mirror image as we did, its OH and CH3 groups now fit exactly on top of the OH and CH3 groups of the original molecule. However, the H and the CH2, CH3 of the two do not match. This one and this one, the H and the CH2 and CH3, they don't match at all. As what we can see, the H is away from us in the original but towards us in the mirror image. The CH2, CH3 group is toward us in the original but away from us in the mirror image. We conclude that the original molecule of 2-butanol and its mirror image are non-superposable and therefore they are different compounds. To summarize, we can turn and rotate the mirror image of 2-butanol in any directions in space. But as long as no bonds are broken and rearranged, we can make only 2 of the groups or 4 groups bonded to carbon, 2 of the mirror image coincide with those on its original molecule. Because 2-butanol and its mirror image are not superposable. They are isomers. Isomers such as these are called enantiomers. Enantiomers, like gloves, always occur in pairs. So objects that are not superposable in their mirror image are said to be chiral. Okay? That is, they show handedness. We encounter chirality in 3-dimensional objects of all sorts. Our left hand is chiral, and so is our right hand. Thus, our hands have an enantiomeric relationship. A spiral bonding or binding on a notebook is chiral. A machine screw with a right-handed twist is said to be chiral. A ship's propeller is chiral. As we examine the objects in the world around you or around us, you will undoubtedly conclude that the vast majority of them are chiral. The most common cause of enantiomerism in organic molecules is the presence of a carbon with 4 different groups bonded to it. Let us examine this statement further by considering the 2-propanol, which has no such carbon atom. In this molecule, carbon 2 is bonded to 3 different groups, but no carbon is bonded to 4 different groups. Again, this carbon here is bonded only to 3 groups. Why? Because OH is one group, H is another, CH3 is another. Notice that 2 CH3s are bonded to your carbon number 2. Notice on the left is a 3-dimensional representation of 2-propanol. On the right side is its mirror image. Also shown are the ball and the stick models for each molecules. Now the question is, what is the relationship of the mirror image to the original? This time, let us rotate the mirror or the mirror image by 120 degrees, about the C bonded to OH. And then, we compare to its original image. After performing this rotation, we see that all atoms and bonds of the mirror image fit exactly on the original. Thus, the structure we first drew for the original molecule and its mirror image are in fact the same molecule, just viewed from different perspectives. To summarize, if an object and its mirror image are superposable, then they are identical and enantiomerism is not possible. We say that such as an object is achiral or without chirality, that is, it has no handedness. Example of chiral objects include an undercurated cup, an unmarked baseball bat, a regular tetrahedron, a cube, and a sphere. To repeat, the most common cause of chirality in organic molecules is a tetrahedral carbon with 4 different groups bonded to it. We call such a chiral carbon as the stereocenter. The 2-butanol has 1 stereocenter, 2-propanol has none. As other examples of a molecule with a stereocenter, let us consider also the 2-hydroxypropanoic acid, more commonly named as the lactic acid. So the lactic acid is a product actually of anaerobic glycolysis. That means it does not require oxygen, and it is also what gives us a sour cream. It's a sour cream taste in our taste buds. Now the question is, how do we specify the configuration of a stereocenter? Because enantiomers are different compounds, each must have a different name. The over-the-counter drug, which we know, the ibuprofen, for example, displays enantiomerism and can exist as the pair of enantiomers shown here. Only one enantiomer of ibuprofen is biologically active. It reaches therapeutic concentrations in the human body in approximately 12 minutes, whereas the racemic mixture takes approximately 30 minutes to achieve this feat. However, in this case, the inactive enantiomer is not wasted. So the body converts it to the active enantiomer, but this process takes time. What we need is a system to designate which enantiomer is ibuprofen or one of any other pair of enantiomers for that matter, is which without having to draw and point to one or the other of the enantiomers. Thus, we do have developed, of course, the RS system. The first step in assigning an R or S configuration to a stereocenter is to arrange the groups bonded to it in order of priority. So the priority is based on the atomic number. The higher the atomic number, the higher the priority. If a priority cannot be assigned on the basis of the atoms bonded directly to the stereocenter, look at the next atom or set of atoms and continue to the first point of difference. That is, continue until you can assign a priority. This slide shows the priorities of most common groups we encounter in organic and biochemistry. In the RS system, a C double bond O is treated as if carbon were bonded to two oxygens by single bonds. Thus, the CH bonded to O has a higher priority than the CH2OH, in which carbon is bonded to only one oxygen. R is used in the RS system to show that when the lowest priority group is away from you, the order of priority of groups on a stereocenter is clockwise, while S is used in the RS system to show that when the lowest priority group is away from you, the order of priority of groups on a stereocenter is counterclockwise. So to assign R and S configuration to a stereocenter, we have these rules. So first, we assign a priority from 1, which is the highest, to a lowest, which is 4, to each group bonded to the stereocenter. Second, orient the molecule in space so that the group of lowest priority, which is number 4, is directed away from you. The 3 groups of higher priority, 1 to 3, then project toward you, as would the spokes of a steering wheel. Read the 3 groups projecting toward you in order from highest, which is 1, to lowest, which is 4, or the lowest priority. If reading the groups 1, 2, 3 proceeds in a clockwise direction, that means to the right, the configuration is designated as the R. From the Latin, that means rectus or straight. If the reading of 1, 2, and 3 proceeds in a counterclockwise direction, or that means to the left, the configuration is S, from the Latin sinister or left. You can also visualize this system as follows. Turning the steering wheel, imagine that you are turning a steering wheel to the right, equals the R. And turning the steering wheel to the left, that means it equals the letter S. Now the question is, how many stereoisomers are possible for a molecule with 2 or more stereocenters? For a molecule with n stereocenters, the maximum number of stereoisomers possible is 2 raised to the nth power. We have already verified that for a molecule with 1 stereocenter, 2 raised to 1 is equals to 2 stereoisomers. That means 1 pair of enantiomers are possible. For a molecule with 2 stereocenters, a maximum of 2 raised to 2 is equals to 4 stereoisomers. That means with 2 pairs of enantiomers is possible. For a molecule with 3 stereocenters, a maximum of 2 raised to 3, that means equals to 8 stereoisomers. 4 pairs of enantiomer is possible. We begin our study of molecules with 2 stereocenters by considering the 2,3,4 trihydroxybutanol with 2 stereocenters. That means it has 4 stereoisomers existing. So the maximum number of stereoisomers possible for this molecule is 4, each of which has been shown in this slide. Notice that the stereoisomers of A and B are non-superposable mirror image and are therefore a pair of enantiomers. Stereoisomers of letter C and letter D are also non-superposable mirror images and are a second pair of enantiomers. We describe the 4 stereoisomers of 2,3,4 trihydroxybutanol by saying that they consist of 2 pairs of enantiomers. So enantiomers A and B are named erythros, and Erytheros is synthesized in erythrocytes or the red blood cells, thus the derivation of its name. Enantiomers C and D are named threos. Erytheros and threos belong to the class of compound called the carbohydrates. We have specified already the relationship between the A and the B and that between the C and the D. The question is, what is the relationship between A and C? Between A and D? Between B and C? And between B and D? The answer is that they are diastereomers, which stereoisomers that are not mirror images. How about molecules with 3 or more stereocenters? The 2 raised to the nth power rule applies equally well to molecules with 3 or more stereocenters. Just like what we have here, the cholesterol, a more complicated molecule, has 8 stereocenters. To identify them, remember to add an appropriate number of hydrogens to complete the tetravalence of each carbon you think might be a stereocenter. Another question is that what is optical activity and how is chirality detected in the laboratory? Before we discuss this thoroughly, let us define words and other concepts of chemistry. Here we have ordinary light. Ordinary light are light waves vibrating in all planes perpendicular to its direction of propagation. When we say plane polarized light, these are light waves vibrating only in parallel planes. And when we say polarimeter, it's an instrument for measuring the ability of a compound to rotate the plane of plane polarized light. And when we say optically active, it shows a compound rotates the plane of plane polarized light. Remember the R and the S configuration in our previous discussions. As we have already established, the two members of a pair of enantiomers are different compounds, and we must expect, therefore, that some of their properties differ. One such property relates to their effect on the plane of the polarized light. Each member of a pair of enantiomers rotates the plane of polarized light. For this reason, each enantiomer is said to be optically active. So, to understand how optical activity is detected in the laboratory, we must first understand how optical activity is detected and what plane polarized light is and how a polarimeter, this instrument, used to detect the optical activity or the works. Remember that ordinary light consists of waves vibrating in all planes perpendicular to its direction of propagation. Certain materials, such as a Polaroid sheet, which is a plastic film that is used in polarized sunglasses, selectively transmits light waves vibrating only in a parallel planes. Electromagnetic radiation vibrating in only parallel planes is said to be a plane polarized. A polarimeter consists of a light source emitting unpolarized light. A polarizer, an analyzer, and a sample tube here. If the sample tube is empty, the intensity of light reaching the detector, when we say the detector, of course, that is our eyes, is at its maximum when the axes of the polarizer and analyzer are parallel to each other. If the analyzer is turned either clockwise or counterclockwise, less light is transmitted. When the axis of the analyzer is at right angles to the axis of the polarizer, the field of view is dark. That means no light passes through. Also, when a solution of an optically active compound is placed in a sample tube, it rotates the plane of polarized light. If it rotates the plane clockwise rotation, then we say it is dextrorotatory. If it rotates the plane counterclockwise, then we say it is levorotatory. Each member of a pair of enantiomers rotates the plane of polarized light by the same number of degrees, but in opposite directions. If one enantiomer is dextrorotatory, the other is levorotatory. Thus, racemic mixtures as well as achiral compounds do not display optical activities. The number of degree by which an optically active compound rotates the plane of polarized light is called the specific rotation and is given the symbol of this one, or the alpha. Specific rotation is defined as the observed rotation of an optical or optically active substance at a concentration of 1 grams per ml in a sample tube that is 10 centimeters long. A dextrorotatory compound is indicated by a plus sign, and a levorotatory compound is indicated by a minus sign in parentheses here. It is common practice to report that the temperature is at which the measurement is made and the wavelength of light used. That means degrees Celsius usually. The most common wavelength of light used in polarimetry is the sodium D line, the same wavelength responsible for the yellow color of sodium vapor lamps. Notice in this structure here, following the specific rotation of the enantiomers of the lactic acid measured at 21 degrees Celsius and using the D line of a sodium vapor lamp as the light source. The optical activity of this is dextrorotatory, that means clockwise. This one is levorotatory, that means counterclockwise rotation of the plane. Now the question is, what is the significance of chirality in the biological world? Except for inorganic salts and a few low molecular weight organic substances, the majority of molecules in living systems, both plants and animals, are chiral. Although these molecules can exist as a number of stereoisomers, almost invariably only one stereoisomer is found in nature. Of course, instances do occur in which more than one stereoisomer is found, but these isomers rarely exist together in the same biological system. Let's focus now on the chirality in biomolecules. So enzymes, like the protein biocatalyst, all have many stereocenters. An example of which is the chymotrypsin, an enzyme in the intestines of animals that catalyzes the digestion of proteins. The chymotrypsin has 251 stereocenters. The maximum number of stereoisomers possible to it is 2 raised to 251. But only one of these stereoisomers is produced and used in any given organism. Because enzymes are chiral substances, most either produce or react with only substances that match their stereochemical requirements. So the question, how an enzyme distinguishes between a molecule and its enantiomer. An enzyme catalyzes a biological reaction by first positioning the molecule at a binding site. So this is the binding site. So the binding site is actually located on the surface of the enzyme. An enzyme with specific binding sites for 3 of the 4 groups on a stereocenter can distinguish between a chiral molecule and its enantiomer or one of its diastereomers. Assume, for example, that an enzyme involved in catalyzing a reaction of glyceraldehyde has 3 binding sites. 1, 2, 3 binding sites. We name it One which is specific to H, a second is specific for the OH, and the third is specific for the CHO. Assume further that the three sites are arranged on the enzyme surface shown in this figure. The enzyme can distinguish the R-glyceraldehyde, which is the normal or biologically active form, from its enantiomer. Okay, from its enantiomer, because the natural enantiomer can be absorbed with three groups interacting with their appropriate binding sites. For the S enantiomer, at best only two groups can interact with these three binding sites. Because interaction between molecules in living systems takes place in a chiral environment, it should come as no surprise that a molecule and its enantiomer or one of its diastereomers elicit a different physiological responses. As we have already seen, the S-ibuprofen is active as a pain and fever reliever, while its R enantiomer is inactive. Also, the S enantiomer of the closely related analgesic naproxen is also the active pain reliever of this compound, but its R enantiomer is a liver toxin. To summarize everything that we have discussed, first, what is enantiomerism? In enantiomerism, of course, a mirror image is the reflection of an object in a mirror. And enantiomers are pairs of stereoisomers that are non-superposable mirror image. A race mixture contains equal amounts of two enantiomers and does not rotate the plane of polarized light. While we have diastereomers are stereoisomers that are not mirror image, and an object that is not superposable on its mirror image is said to be chiral. It has handedness. An achiral, on the other hand, it's an object lacks chirality or handedness, that is, it has a superposable mirror image. The most common cause of chirality in organic molecules is the presence of the tetrahedral carbon atom with 4 different groups bonded to it, such a carbon called as a stereocenter. Then, how do we specify the configuration of a stereocenter? We use, of course, remember, the RS system. So the RS system is to specify the configuration of a stereocenter. Also, how many stereoisomers are possible for molecules with 2 or more stereocenters? Of course, for a molecule with an N stereocenters, the maximum number of stereoisomers possible is 2 raised to the nth power. What is optical activity, and how is chirality detected in the laboratory? Light with waves that vibrate in only small planes is said to be plane and polarized. We use, of course, a instrument which is known as polarimeter. A polarimeter, it's a compound wherein a compound is said to be optically active if it rotates the plane of polarized light. If a compound rotates the plane clockwise, it is dextrorotatory, and if it rotates the plane counterclockwise, it is levorotatory. And each member of a pair of enantiomers rotates the plane of polarized light an equal number of degrees, but in opposite directions. Lastly, what is the significance of chirality in biological world? Of course, earlier we discussed enzyme. An enzyme catalyzes biological reactions of molecules by first positioning them at the binding sites on its surface. Enzyme is very important in reactions in our body because it catalyzes different reactions in the body. An enzyme with binding sites specific for 3 of the 4 groups on a stereocenter can distinguish between a molecule and its enantiomer or one of its diastereomers. So that ends my presentation. Thank you for your kind attention. God bless and keep safe, everyone.